All right. So in this lecture, I'm going to introduce chapter 4 of the textbook. This lecture will be in two parts. I'm going to first introduce the first half of the chapter right up to before logistic regression. Then in the second part, I will talk about logistic regression. Let me share my screen here. Right, so these are the slides, and where we are at with the textbook is that we have already looked at the foundational ideas in the introductory chapter, and then looked at Bayes' rule. We've fit some simple linear models, very simple linear models with just one intercept, for example, using BRMS, which is the front end first 10. And now we are going to start looking at slightly more complicated models in chapter 4, where we will have a predictor that can modulate uh, the dependent variable. So this is an important framework because so this is the standard framework that you're probably all familiar with. I still have to go through it once so that we are all on the same page, right? So we are going to be working with this kind of situation where you've got, or shall I use alpha here? There are different conventions for how to represent the intercept. So I'll just call this alpha and call this beta times x plus epsilon. So this will be the general framework that we are going to talk about today. And then I'm going to start elaborating on this framework by adding um, more structure to the linear model. And that will bring us to the so-called linear mixed model or the hierarchical. Okay, so coming back to the slides. So the problem that we are going to look at, the scientific problem that we're going to look at is a kind of experiment design where the subject has to track multiple objects on the screen. And so at the start of the trial, several objects appear on the screen, and then the subject is shown which objects are of interest, which ones have to be tracked. Then the objects start moving, and the marking on the subjects that have to be tracked is removed. So the subject's job is to keep track of those dots that were marked as targets for tracking. And then after some time, the objects stop moving, and then the subject has to indicate, for example, with a mouse, with a button press or something on the mouse, that which of the, they have to indicate which of the objects are the target, were the targets, right? So here what they do in this experiment is that the number of dots can be decreased or increased. And so if you increase the number of dots, then the attentional load will increase. And the dependent variable in this experiment is pupil size. So pupil size is measured with an eye tracker, which can measure the diameter of the pupil. And the unit in which the diameter is measured is some abstract unit. So it's not millimeters or centimeters or something like that. So you will see large numbers, but those numbers have some internal meaning in the context of the software and hardware that is used for tracking the eyes, right? So the dependent variable is a continuous value, and um, I just need to make sure. Again, I keep forgetting whether I started recording. Yes, sorry. So, so we have a continuous dependent variable, and so we're going to work with a standard linear modeling framework with that, with this setup, right? So this is what it looks like, what the experiment looks like. You start with a fixation. Generally, you get the subject to fixate on the center of the screen because you don't want the subject to start each trial by looking somewhere at random on the screen, right? You always want the same starting point for each subject. And then the dots appear, and the targets are designated. You can see those designated targets. And then the, the designated targets are no longer distinguishable from the other circles, and then everything starts moving. So for 8 seconds, the subject's job is to track the target, and then once the 8 seconds are up, then you have to, for example, press a button to indicate which two circles were the targets that had to be tracked. Okay, so that's the setup. So a simple model for this kind of setup would be to have pupil size. So n, remember that n is always the nth row in the data frame, right? So every row in the data frame, the pupil size is being modeled as a coming from a normal distribution with some intercept and some slope. And what I've got here is centered load. So I'll just explain that in a moment. But we're going to always center the predictor whenever we fit these linear models. So the rest is all clear because we got a Gaussian distribution. You got some intercept. So the intercept is this thing here, right? The value of the intercept will depend on the level of the load that is set up in the experiment. So I'll just show you the data frame in a moment. And sigma is, of course, the residual standard error, right? All right. So we are assuming for now that every data point in this vector is independent. So in frequentist terms, that it's independent and identically distributed. In other words, uh, what I'm assuming here is that I do not have repeated measurements from each subject in each load level condition, right? So remember that the loads are going from 0. How can it be 0? I'm sorry, maybe I'm wrong about this. So maybe it's like 1 to 5 objects or something like that. So I will just check that as soon as we load the data, what the range of the objects are that are being tracked. Because if you have 0 objects on the screen, um, I'm not sure how that trial would actually play out. In any case, let's just take a look at the data, right? So where was I? Yeah, so I'm assuming that the pupil size is independent and identically distributed. So let's just quickly take a look at the data. Um, this is chapter 4 here, right? Right, so we have to load all of these in the setup here so that I can run all the functions, and then I have to, yeah, here's my Um, this is some pilot data. Let's see. Okay, so let's start with, let's look at the actual data first, okay? So I'm just gonna do that. I'm gonna load the pupil data. So let's look at the DF pupil. Actually, it never hurts to look at the data before starting to analyze it. Not something that people do very often. All right, so what we have here is that each subject is giving me a certain amount of data for each load level, right? So one question that I would have when I'm starting to do the analysis in real life, if I were actually doing this analysis, I would want to know if I have exactly one data point from each subject in each load condition. So I could do that like this, right? Right, so what I see here is that these data are actually from a single subject, and this single subject is delivering repeated measurements, on um, on the for each of the load levels. So I certainly am surprised that there's a load level 0. So anything non-zero I can understand, but I'm not really sure what it means to be 0. I think I've forgotten what the setup for the experiment is. But in any case, there are 6 levels here, right? And we have repeated measurements for each level from this subject, right? So normally if you were to really do this experiment in real life, this is probably just a subset of the real data. In real life, I would have multiple subjects and each subject is then delivering multiple data points for each of the levels. And the reason I have one less data point in the fifth condition is probably that some data were deleted, either lost during data collection or deleted due to the data point being, um, the data point being an influential value or something like that. So here I would be a little bit, worried about treating the data as independent and identically distributed, but I'm doing it anyway, right? And the reason for that is that we want to start simple. Okay, so we know that this model is probably not correct. Maybe there is some structure in the data that we should be modeling, especially if we have multiple subjects. But that's a topic that I will come to in chapter 5. Right now, we are ignoring the fact that we are not modeling the full structure in the data, the repeated measurements, the dependencies in the data points, but we'll just treat every single data point as independent from every other data point, knowing that this is not technically true here for pedagogical reasons. Okay, so let's just um, let's just step away from reality for a moment and simplify our world just to understand the models better. All right, so before we get started with the modeling in the Bayesian framework, right? In the frequentist framework, this would be easy. Like I would just basically fit this model in a simple LM framework. In the Bayesian framework, we have to think about the priors. And so one way to think about what priors use could be to have some pilot data, right? And that we have in the library associated with the book. You could use some pilot data to figure out what the general range of the observed data are. So this is not the same data that we are going to analyze, but this is data that we collected as pilot data before actually running the experiment. Okay. So, so if I look at the pilot data and look at this, the six number summary of the pilot data, I see that the range is from 852 to 868. And so this basically allows me to start with some kind of regularizing prior for the intercept, right? So I'm assuming that the intercept has a prior with mean 1000 and range 500. So that allows a prior like this allows the what it means graphically. What it actually means graphically is that, right? So a normal distribution prior with mean 1000 and standard deviation 500 means that with 95% probability, I'm between 1000, between 0 and 2000, right? Because 2 times, what was it? I already forgot the standard deviation. 500, right? 2 times 500 gives me 1000. So if I go 2 times 500 this way and minus 2 times 500 this way, I end up at 0 and 2000. So that's a regularizing prior in the sense that it downweights such low values and such extremely high values here. And so the most likely data will be in this rough range. The prior is somewhat broad in the sense that it allows more variability than we have observed in the pilot data. But that's because I wouldn't take the pilot data as, as the gold standard or as the truth or anything. It's just a starting indicator of the rough ballpark of the values that we should be observing in the actual experiment. So it's a good starting point here. Okay. So oh, here, sorry, I actually did the exact calculation of the 95% credible interval. It's not exactly 0 and 2000, but it's roughly in the same range. So that's a reasonable starting point. For sigma, we could use an uninformative prior for starters, right? Because we don't really know that much. Of course, we could use the pilot data to make a start, but let's just take a truncated normal, truncated at 0 with standard deviation 1000. So once you truncate it at 0, so only consider the positive half of a normal distribution, then of course the mean will shift. And so you can you can look at the quantiles of the 95% credible interval in the situation where you've got a truncated prior. So the truncated prior for the standard deviation assumes a standard deviation from 31 to 2241, which seems like a reasonably broad range, but not too crazy. Okay. Now, the interesting thing is that in our model, we also have a slope parameter. So we could start with a normal prior with mean 0, standard deviation 100. That allows a variation of plus minus 196 with 95% probability, right? That's how we interpret the meaning of the intercept by looking at the range of variability that the prior is assuming. Okay. So now coming to the actual data frame. So as I mentioned, what we're going to be doing is we're going to be analyzing the data on the centered load. Remember that the load column ranges from 0 to 5, right? We just saw that. And so centering the load means that we are going to take the load column, right? So the load column can have values ranging from 0 to 5, and we will subtract from the load column the mean of the load column, right? So once we subtract the mean from each cell in the load column, we're going to get a centered load column, right? And the centered load column will have the property that if the value is 0 in the centered load, that means that this number and the mean load is the same, right? And that means that 0 has the meaning in the centered load column. 0 has the meaning that that's the average load, right? A positive value in the centered load column will mean that the load is higher than the average value, and something lower than 0 negative values would tell us that the the load value is lower than the average, right? So that's what centering is doing here. So that's pretty straightforward, right? So now you can of course see that once you center the load, it goes from, from whole numbers, it goes to real numbers now because we are subtracting the mean from it, right? And there might be some imbalance in the data, which would result in a non-whole number mean, right? So so that's how you end up with these decimal points here for the load. So the load is being treated as a continuous variable here. Okay, that is important, very important to understand that load is a continuous variable here. So this standard linear model again is pretty straightforward. I don't need to explain this. Here are my three priors. This all discussed earlier. This is the Gaussian likelihood here, and so what would be interesting to see here is the posterior distributions of the three parameters, the intercept, slope, and standard deviation, right? So we can look at that here. And we can see the chains are converging nicely. And we've got the estimates of the parameters here, right? And you can see that the posterior distribution of the intercept, which is representing the average um, pupil size, oh, sorry, it's representing the pupil size when the load is at its average value, right? So I hope this is clear. What the intercept means here is that what the intercept means is that if I have like beta times centered load, right, plus epsilon, right? So when centered load has the value 0, that has the meaning that this is the average load, right? Therefore, when this value is 0, centered load is 0, this whole term is going to be 0. Therefore, alpha, actually, the intercept actually represents the expected or the estimated um, pupil size when the load is at the average value. Okay, and so what the meaning of the beta parameter is now is that for every unit increase in load, what is the predicted increase in pupil size? And you can see that the pupil size will increase between, let's say, 10 and 50 or something like that for every unit increase in um, in load. Sigma is just the residual standard deviation posterior, so that's pretty straightforward. And you can use this short summary function that I've written, that is written into the slides. It's not visible, but there's a function at the very top in the slides, the code that comes with the slide for producing this short summary, which strips out all the redundant information so that it all fits on one slide, right? So what we are looking at here is the posterior distribution summary. So the intercept and slope estimates, the standard deviation estimates, and the 95% confidence interval. This is like the most important information that I get out of a Bayesian analysis, the posterior estimates, the summary statistics on the posterior. Yeah. I generally ignore the standard error. I don't even know why they actually print this out. I've never felt the need to look at this and or interpret this at all. I'm really interested in the posterior distribution of the parameters, and the lower and upper bounds of the credible interval are very important, indicators of the uncertainty of these parameters. Because Bayesian statistics is all about uncertainty quantification. We are very interested not just in the mean, but we're interested in how variable the estimate is of the parameter of interest. And so that summary is given here. These details I'll discuss at some point, but not right now. Okay, so here's what we can now do is we can generate posterior predictive distributions by plugging in different values for centered load. If you put the centered load value at 0, that means average load. No, sorry, let me start over. So what you're seeing right now is not the centered load, but the actual load levels, 0, 1, 2, 3, 4, 5. What you can do is you can plug in the equivalent value into the linear model for load equal to 0, right? Or for load equal to 1, right? You would have to plug in the equivalent centered load value into the linear model to get the value for any particular load level, right? I hope that's clear. And so now what's being generated here is the observed data is the black line, and the blue data are the posterior predictive distributions that are produced. You can also run this code yourself and see how it all is playing out in detail. Okay, so you should look at the code later on. Similarly, you can do the same for load 1, load 2, load 3, load 4, and load 5. So I didn't have load 5 here, I don't know why, but so this gives you a good understanding of what kind of data the model is producing. And it seems that even though the posterior predictive data are pretty noisy, you can see these huge peaks here, like they don't look really super realistic. But so they are certainly noisy, but they're still roughly in the ballpark. I have seen much worse. Okay, as with experience, you will learn to interpret whether your posterior predictive distribution is completely off the charts. Like it doesn't make any sense. And later on, you will see lots of examples where the posterior predictive distribution is completely way off from the data. It doesn't make any sense at all. So that can happen. And that can happen, for example, if you have the wrong likelihood function. All right, so let's look at another example here. Same data set that um, we had earlier, right? So the button pressing time data, but this time we'll look at the effect of trial ID, right? So I'm stepping away from the multiple object tracking experiment now and going back to the chapter 3 button pressing data. And there we had, in chapter 3, we had only looked at the intercept, tried to model the intercept to get the average button pressing times. Now we are going to look at the effect of trial on button pressing time. And we are going to work with the log normal likelihood. So this elaborates the linear model a little bit by stepping away from the Gaussian likelihood and adds a predictor to the model. So there's two complexities that we've added to the linear model here, right? So first we take same thing as before. We had centered load. Now we're going to center the trial ID as well. The trial ID is a number going from 1, 2, 3, 4, 5, all the way up to the number of trials in the experiment. And centering simply means that you subtract from each element in the trial column the mean of the trial. So you get a continuous value for this centered trial predictor, right? This has the advantage that the intercept now has a meaningful interpretation, right? It means the intercept now represents the predicted button pressing time when you have an average trial ID. Otherwise, if you did not center the trial column, right, if you work just with this trial column, then the meaning of the intercept would be somewhat unrealistic, because then the intercept means that when the trial ID is 0, the predicted button pressing time is whatever it is, right? Whatever the intercept estimate is. But trial ID will start with 1, it won't start with 0. So it's outside the range of possible trial ID, right? So that makes the intercept less interpretable. And that's why it's interesting and useful to actually center the predictor here. That's one reason why centering is useful. It makes the intercept easier to interpret. All right, so we're going to now assume that our button pressing times, I should have called this T, I guess, right? Let's fix that right now. Okay? I should have called this T to be consistent with the chapter 3 notation, right? So this will be fixed once I recompile. So for every button tapping time in the nth row in the data frame, I'm assuming that the data are coming from a log normal. So this is just like the model I just fit for the multiple object tracking, but in the button pressing scenario and with a log normal distribution, right? So let's proceed and see where we go with this, right? So as I mentioned in my previous lecture in chapter 3, because we are working with the log normal likelihood now, the intercept and the slope and the standard deviation will have to have the parameters defined on the log scale. So I'm assuming here that the intercept has a normal prior with mean 6 and standard deviation 1.5. Okay, so because of the log normal likelihood. And similarly for the sigma parameter, I have a truncated normal, standard normal prior. Now, the interesting thing is, what do we do with the beta parameter? And what kind of prior should we define for the beta parameter? Well, you could start with an uninformative normal 0, 1 prior. This is very uninformative because if you try to generate, some data from such a distribution now, from the log normal likelihood with these priors, you will find that there will be a dramatic amount of variation, right? So let's take a look at what happens when we assume such an uninformative prior, how to evaluate, the consequences of such a prior specification. So let's take a look here. We do some prior predictive modeling now. And so what we're going to do is fit the model. So this is button pressing time, 1 plus centered trial, right? And notice that this is again using a fake data frame here. This created a fake data frame here with an empty column called RT. This is all a big mess right now. I'm sorry, there's been some inconsistency in the coding here. This should have been T, it should not have been RT, but doesn't matter. It doesn't really have any impact on what's about to happen here, because this is just a dummy data frame. And what we are trying to do is we are going to produce prior predictive data. That's why we have sample prior equal to only. We are not looking at any data here while generating data from the model. So it's producing data from this prior predictive distribution here, given this model specification with this particular likelihood. Okay, that's what this sample prior only function does for us. Right? It's sampling only from the prior, not looking at any data. And so what we are computing here is the median difference between every button pressing time and its adjacent button pressing time. right? So between every button pressing time and its adjacent button pressing time, there will be some difference, and that difference will keep varying from trial to trial. So if you take the median difference, right, you will in multiple generated data sets, you will see a distribution of the median differences. So that's what we are computing here. We're computing the median difference statistic, and so that's a function that is defined by you. So you can decide which function you want to investigate in your prior predictive distribution, and write that function in here, in this case median difference. And now, using the PP check function, if you look at the median distribution of median differences, what you notice is that the range of median differences is really large. It's going from uh, 5 to the 5 times 10 to the times 10 to the power of 4 is the upper bound, and the lower bound is -1 times 10 to the power of 5. So those median differences are really huge on the millisecond scale. Doesn't make any sense actually, right? So what that means is that our beta prior is too broad. This beta prior is way too big. Okay, so we're gonna make this a little bit tighter, and then see what that does for us, right? So let's change the beta prior. This is on the log scale. Okay, these numbers look small, but they are not as small as you think they are, because they're happening on they are interpreted on the log scale. So now I set up a more informative prior, and let's see what this gives us. Okay, so again we are going to do the same thing. We fit the model again, and this time we are using a more informative prior here, right? That's the only thing that's changed. And now if you look at the median differences in the prior predictive data, you'll see that the median differences are not so dramatic anymore. They're going from 1000 to +1000, some more extreme values here and there, but this is a lot more reasonable if you compare it to this range here. Okay? This range is incredible. So, so this would be reasonably acceptable as a prior predictive distribution, because it's still in the ballpark, it's not too crazy. Of course, you could also look at the data to see, or look at maybe previous data to find out what the range of median differences would be. I wouldn't be using the current data to decide, what prior to use for my model, because the prior by definition is determined prior to analyzing the data. So if you look at the data that you're about to analyze, use that to decide on your priors, and then define the priors accordingly. That is, I think that is not in the spirit of the Bayesian approach. Technically, of course, you can do that, but you shouldn't do that, right? It's prior predictive, prior specifications are not supposed to be derived from the very data that you're going to now analyze. All right. So in this situation, having decided on our priors, we start to now fit the model. So because we are willing to allow this much, variability in the median differences, it's not so crazy. So you fit the model. This time we are fitting the actual data. You see this, right? Earlier I was using just a fake dummy data set. There was a dummy data set there. So now we are fitting the actual data, and with a more informative prior. And when now I look at the posterior, and now what I see is the intercept is ranging on the log millisecond scale, right? It's ranging from about 5.1 something to 5.1 something. So the decimal points are missing here, so it looks like 5.1 everywhere, but obviously there is some variability there. And we are also seeing some small value for the slope parameter on the log scale, of course, right? Similarly here also. So the numbers have, of course, changed, because compared to the case when we fit a Gaussian likelihood, but I hope that it's clear what's going on there. So now the issue is, having fit the model on the log milliseconds on the log scale, we, as researchers, it's harder for us to interpret the data on the on the log scale. So it would make more sense if we could somehow back transform the data to the millisecond scale so that we could interpret, what these parameters actually mean on the millisecond scale. So the back transformation that is pretty convenient as an approach is to first extract the samples for the intercept and for the slope. Okay, so now I've got the samples for the alpha and the beta parameters. These are on the log scale. If I want the beta parameter um, to, right, so what I want to know is what is the estimated change in button tapping times when I go from the average value of the trial between the trial before the average value of the trial to the average value of the trial. So what I'm doing here is this term here, this exponent of the alpha samples is computing the median button tapping times when you're at the average value of the trials. Whatever the average is for the trial ID, um, the expected the expected median button pressing time is this number here, okay? Whatever this, or not this number, but this posterior distribution on the millisecond scale. So what's going on here is the following. So what I'm doing here is that I've got my button pressing times which are on the log scale, right? They're on the log scale. And I've got an intercept alpha, and I've got a slope for the centered trial, right? Now, when the centered trial value is 0, then this whole term disappears, right? Therefore, when the centered value is 0, the expected um, um, button pressing time is log t, right? When centered trial is 0, right? So now if I exponentiate both sides, I'll take the exponent of this side and the exponent of this side, right? What I end up with here on the left-hand side is the expected button pressing time in milliseconds. So I'm back transformed to the original scale that I can actually interpret as a human being, right? So this exponential transform, this gives me the median, not the mean. We don't use the mean generally because the mean in the back transform from the log to the millisecond scale will involve the standard deviation. It's a formula that's discussed in the textbook, but it complicates the calculation quite a lot. And the median is actually a good thing to calculate because it's a much more stable value. And so it works well for our purposes as a back transform. So what we are getting back is the median um, button pressing times when the trial ID, the center trial ID, has the value 0. So that's what's happening here. I'm sorry, not here. That's what's happening here. That's that calculation. That's telling me, it's giving me the posterior distribution of the alpha samples back transformed to the millisecond scale. So I've got the median values here. And I'm subtracting from that the effect of going from centered trial ID 0 to centered trial ID -1. That means the trial ID preceding the average trial ID would be trial ID, centered trial ID -1, right? So that's why you've got alpha samples minus beta samples, and then take the exponent of that. So what's going on is the following. Let me write this down. The kind of computation I'm doing here is that when centered trial is 0, so let me write that. When center trial is 0, then my model is um, log t is equal to alpha, right? So my estimate of alpha, whatever my posterior distribution of alpha is, that is the posterior distribution representing the average button pressing times when the center trial ID is 0, right? And so what I do is if I want to interpret that alpha value at on the millisecond scale, I exponentiate it, right? Now, similarly, when the center trial ID is not 0, but -1, right? What would the model look like now? It would be log t alpha plus beta times -1, right? Because the center trial value will now be -1. And that is just the same thing as writing alpha minus beta, right? Now, if I want to exponentiate both sides, I'm going to exponentiate both sides, right? If I exponentiate both sides, I end up with this term here, alpha minus beta, right? Which is now telling me on the millisecond scale, right? It's telling me the expected button pressing time for the center trial ID being -1, right? That's what it's giving me. So what that does is, if I take the vector, this is a vector, right? Because this is a posterior distribution. This thing was, if you remember in the code, alpha samples are the 4,000 samples from the posterior distribution. So when I'm writing alpha here, I'm talking about those 4,000 samples. So I'm exponentiating those 4,000 samples. So if I take those 4,000 samples and subtract from them alpha minus beta, what this gives me is on the millisecond scale, it's giving me the expected change um, in button pressing time as I go from the um, as I go from the trial preceding the average trial to the average trial ID. As I go from the trial ID preceding the average trial ID to the average trial ID. So that's this back transformation is giving me, what this is giving me is on the millisecond scale, the effect of transitioning from one trial ID to the subsequent trial ID, where the subsequent trial ID is the mean ID, trial ID in the centered column for centered trial. Okay, so you can calculate statistics now. This is a posterior distribution now, right? This is actually a distribution because it's a transformation of the posterior samples for alpha and the posterior samples for beta. So these are 4,000 samples each. So we're getting back a vector that represents the beta, the transformed value of the beta parameter on the millisecond scale. So now we can interpret it. That's the whole point, you know. The whole point here is that we should be able to interpret the beta parameter in terms that we can understand as researchers. So that's what the back transform is for. And once you have that vector, you can calculate statistics on it, like the mean and the lower and upper bounds, right? So these are 95% credible intervals. So what you get is the mean of 0.087 milliseconds and with a credible interval of 0.06 to 0.1. So these numbers are very small on the millisecond scale because we're talking about the change in the button pressing time when you go from one trial to the next, right? So So right now, the example that I was showing you here was looking at the change in the button pressing time, this one here, this calculation that I've done here, when we go, when we are in the middle of the experiment, because we are always talking with reference to the center trial ID, that is the average trial ID, and we want to know what happens when we go from center trial ID to from the trial ID preceding the center trial ID to the center trial ID. That's what we're getting here, right? But we could do the same calculation for any location in the experiment. So we could look at the effect estimate in the first versus the second trial. You can do that, no problem, right? So how would I do this? First, we find out what the first trial ID's numerical value is in the center trial column. That would be the minimum value in the center trial column, right? That would represent the first trial ID. The second trial ID would be whatever the minimum is plus one, right? So now we are looking at the change in button pressing time as you go from the first to the second trial ID, right? So now again, we are doing the same calculation, but this time we are, so we are computing the effect of the change in the button pressing time when we go from the first to the second, okay? So, so this first line here, what it's doing is it's taking the alpha sample plus the beta samples and multiplying it with the numerical value, what this numerical value, whatever it is, right? Whatever this number is. And so let me do this, okay? Let me do this by hand. So suppose, so why should we suppose? Let's actually do this, okay? Let's just do this. Let me just find the data frame. Right, so this is the data frame. Is it already there? Yeah, it's there. It's good. So now I've centered, yeah, I've centered the data frame, the trial ID. So let's take a look. So here's my centered trial ID. And so let's see what the minimum value is. Minimum value for centered DF space. What's wrong here? Space bar, sorry. Space bar. Minimum value is minus 180. Minus 180 corresponds to trial ID 1, okay? And therefore, this thing plus 1 would correspond to trial ID 2. So what I'm going to do now is I've got 100 minus 180 and minus 179 is my centered values. So what I have is my button pressing time on the log scale, right? And so there's an intercept. And what I have is the intercept and slope. These are the posterior distributions of the parameters. So these are actually vectors of length 4,000 because I have 4,000 iterations in the samples, okay? There's 4,000 samples here. So what I'm going to do is I'm going to, to compute the predicted button pressing time in the very first trial, I'm going to take those posterior samples, right, and multiply the slope with minus 180, which represents the first trial. Right? This is my expected button pressing time for the first trial, and this is my button pressing time for the second trial. Right? So I have two values here in the boxes that I've just drawn that represent the button pressing time for the first trial and the second trial. So what I'm going to do is I'm going to take the second button pressing time. and subtract from it the first button pressing time, but I'm going to do it on the millisecond scale. So what I'm going to do is I'm going to exponentiate both the terms. So how do I do this exactly? What am I trying to do here? I'm going to take this second value here, alpha plus beta times minus 179, right? Exponentiated minus exponentiated alpha plus beta times minus 180, right? So this will give me a vector of 4,000 scores on the millisecond scale, which represents the change in the button pressing time when I go from the first to the second trial. So that's what's going on here. That's what this code is doing. You see that? Second minus first trial. Okay. So these numbers are, this is one minus 179, this is minus 180, and so on. So now I can compute statistics, summary statistics, and what I see is that the change is this range. This is the mean, and these are the 95% credible intervals. Now, this is again very hard to interpret because there's a very small change in button pressing time. This is on the millisecond scale, okay? 0.079 milliseconds. So you could also ask questions like, what is the slowdown that, or what is the change in button pressing time that you would see when you go from the middle of the experiment to 100 trials downstream, right? You can do that by computing the effect 100 trials downstream, by computing the estimate for the value 100 times downstream from the middle of the experiment. So 100 times beta samples plus alpha exponentiated minus the expected button pressing time at the average point at the middle of the experiment, right? So that's pretty exactly what we have done earlier, but just doing it with any range of values, that you might be interested in. So this is easier to understand now because what this tells us, if I do this calculation on the millisecond scale, we basically observe a 9 millisecond slowdown on average as we go from the middle of the experiment to 100 trials downstream. So there is a fatigue effect that we are seeing here, okay? And the 95% confidence interval is 6 to 11 milliseconds. Now this is much easier to understand from a human perspective, right? So what I'm trying to show you here is that once you fit the model on the log millisecond scale, on the log normal likelihood, with the log normal likelihood, you can always go back to the original scale to make it more interpretable. And the way you would do that is by back transforming the model's predictions for particular values of the predictor. That's the key point, right? For particular values of the predictor, you can back transform the estimates to a scale that you can interpret. So, so here's the posterior predictive distribution, the distribution of predicted median differences between the nth and the 100th trial, n plus 100th trial, right? So, so this is, you're generating multiple posterior predictive data sets. Each posterior predictive data set will have some, um, uh, some median difference between the center point of the trial and the 100 steps downstream. And so if you have multiple data sets, you're going to get a distribution of medians. And so that's what you're seeing here. And this is the actually observed median value in the data, the black line here. And these are the generated values from the posterior predictive distributions. And you can see that they're pretty reasonable. The model is producing pretty reasonable median differences between the nth and the n plus 100th trial. Okay. All right, so that's basically the most important topics that I wanted to get through in um, in this part of the lecture. So just to summarize what I have covered today. So the important ideas that I wanted to get across in this lecture are, first of all, fitting a model with a particular predictor X, but always centered. Centered, why? Because the intercept is easier to interpret, right? And then the next thing I showed you was how to use the log normal likelihood in this scenario, right? And the complication there is that if you take a log normal likelihood, I'm just writing it like this, but you know exactly what I mean, right? Because if I write log normal and I write alpha plus beta times x plus epsilon, right? Or let me write it like this. Let me rewrite this, sorry. So if I'm assuming that the data are coming from the log transform data are coming from a normal distribution, right? Something like this. This is the same thing as saying that y is coming from a log normal with the same parameters alpha and beta times x times with sigma as the standard deviation. So so what the important thing I wanted to discuss, what that I discussed with the log normal distribution was that once you have fit the model and obtained the posterior distributions of these parameters, right? You now want to interpret those parameters on a scale that you can actually understand as a human being, and you can always exponentiate, use the exponential function to get back the predictions for particular values of x, for different values of x. You can derive the expected value of the uh, dependent variable uh, through the model's posterior distribution. That was the important idea that I showed you. And of course, then there was the other important idea of deciding on the priors, right? Deciding on priors. One important step for doing that is prior predictive distributions, right? And an important sanity check after you've observed the data is the posterior predictive distributions, right? So these can all be very useful. Of course, I guess I shouldn't have written it like this. So let me rewrite this. Sorry. What I want to say is that for making decisions about the priors, you want to look at prior predictive distributions because that helps you decide on what a reasonable prior or reasonable sets of priors are going to be, right? So sensitivity analysis is useful there. And for basic model evaluation, right? To understand the behavior of the model, then after seeing the data, the posterior predictive data can be very useful. And you can investigate posterior predictive data uh, in the following way. So you don't necessarily just draw the PP check curves. You can also look at particular um, 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 differences between different levels of your predictor variable. You know, for example, trial ID, center trial ID 0, center trial ID 0 plus 100. Those kinds of posterior predictive distributions, any statistic that you're interested in could be looked at in the posterior predictive distribution. That was the important idea that I wanted to get across here. In the next part of this lecture, I'm going to talk about logistic regression, which is a very important topic in generalized linear models. And well, as you will see later on, logistic regression turns up in hierarchical models as well. So these are called generalized linear mixed models. So the machinery that we learn in this chapter for the logistic regression and the machinery we'll learn in chapter 5 for hierarchical models in general, those can be combined to put together generalized linear mixed models that involve logistic regression. So that will come up later on. Okay, so that's it for today. We'll continue this lecture in a second part.